The arrival of the interstellar object designated 3I/Atlas has offered scientists a rare and valuable opportunity to observe material formed beyond the boundaries of our own solar system, while simultaneously exposing the persistent gap between evidence-based science and public speculation. As only the third confirmed interstellar object ever detected passing through our solar neighborhood, following the discoveries of 1I/Oumuamua in 2017 and 2I/Borisov in 2019, 3I/Atlas has naturally drawn global attention. However, unlike the narratives circulating across social media platforms and fringe commentary spaces, the scientific consensus surrounding 3I/Atlas is both clear and grounded in extensive observational data. It is a natural interstellar comet, following a one-time trajectory through the solar system, and it poses no threat to Earth. The object was first detected on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System (ATLAS), a network specifically designed to identify near-Earth objects and potential impact risks. Almost immediately after its detection, orbital calculations revealed a defining characteristic that set 3I/Atlas apart from the vast majority of comets and asteroids observed by astronomers. Its orbit was hyperbolic, meaning that its velocity exceeds the escape velocity of the Sun. In practical terms, this indicates that the object is not gravitationally bound to our solar system and originated from interstellar space. Once it completes its passage around the Sun, it will continue outward indefinitely, never to return. This hyperbolic trajectory is not a matter of interpretation or conjecture. It is a direct result of precise astrometric measurements collected by observatories across the world. Independent analyses by NASA, the European Space Agency, and multiple international research institutions all converge on the same conclusion. 3I/Atlas entered the solar system from a direction inconsistent with any known long-period comet reservoir, such as the Oort cloud. Its incoming velocity and trajectory firmly place its origin beyond the Sun's gravitational domain. Following its discovery, 3I/Atlas became the subject of an unprecedented multi-instrument observational campaign. Space-based observatories, including the Hubble Space Telescope, the James Webb Space Telescope JWST, SOHO, Stereo, and Punch, were directed toward the object, alongside some of the world's most powerful ground-based telescopes. These observations were not limited to simple imaging. They encompass spectroscopy, polarimetry, photometry, and long-term tracking of its motion and activity. One of the earliest confirmations to emerge from these observations was the presence of a coma and tail, hallmarks of cometary behavior. As 3I/Atlas approached the inner solar system and experienced increasing solar heating, volatile compounds within the object began to sublimate, transitioning directly from solid ice to gas. This process released dust and gas into space, forming a diffuse coma around the nucleus and a trailing tail shaped by solar radiation pressure and the solar wind. This behavior is entirely consistent with what scientists expect from icy bodies, both within and beyond our solar system. Crucially, these features immediately distinguished 3I/Atlas from Oumuamua, which displayed ambiguous outgassing signatures and lacked a visible coma at the time of observation. In contrast, 3I/Atlas behaved in a manner that closely aligns with established cometary physics, reinforcing its classification as a natural object rather than something anomalous or artificial. The most detailed insights into the object's composition came from high-resolution spectroscopy, particularly observations conducted by the James Webb Space Telescope. JWST's infrared instruments revealed a coma dominated by carbon dioxide (CO2), accompanied by smaller but detectable quantities of water vapor, carbon monoxide, and trace organic compounds. While the dominance of CO2 is unusual compared to many solar system comets, where water ice typically plays a larger role, it is not unprecedented. Instead, it suggests that 3I/Atlas likely formed in a colder region of its parent star system, where carbon dioxide ice could remain stable during the object's early history. This chemical profile provides a valuable window into the diversity of planetary systems beyond our own. It supports the idea that comet formation processes may vary significantly depending on local conditions, such as temperature gradients, discomposition, and stellar radiation environments. Rather than indicating anything artificial, the chemistry of 3I/Atlas reinforces its status as a primitive remnant of planetary formation, preserved for billions of years in interstellar space. Additional insight into the object's physical properties came from polarimetric studies, which measure how light is scattered by dust particles in the coma. These studies revealed negative polarization features that are uncommon among typical solar system comets. While this finding initially attracted attention, scientists caution against overinterpretation. Negative polarization can arise from differences in dust grain size, porosity, and surface texture, all of which may reflect formation in an environment distinct from the early solar nebula. Importantly, these properties are still well within the range of natural physical processes and do not imply any form of artificial structure or engineering. Throughout its passage, astronomers closely monitored 3I/Atlas for signs of non-gravitational acceleration, subtle deviations in motion caused by asymmetric outgassing. Such effects are well documented in comets and can sometimes lead to speculation when not properly contextualized. In this case, the measured accelerations were small, predictable, and entirely consistent with gas jets produced by solar heating. No evidence emerged of controlled maneuvering, propulsion, or behavior inconsistent with natural physics. Despite this extensive body of evidence, public speculation surrounding 3I/Atlas intensified as it approached its closest point to the Sun and Earth. On December 19, 2025, the object reached perihelion and its closest approach to Earth at a distance of approximately 1.8 astronomical units, or about 270 million kilometers. This distance places it safely well outside Earth's orbit and far beyond any conceivable impact risk. Orbital simulations extending decades into the future confirm that 3I/Atlas will continue on its outbound hyperbolic path, gradually fading from view as it exits the solar system. Nevertheless, sensational headlines and viral social media posts began to circulate, claiming that the object's trajectory had changed, that it was coming back, or that it represented alien technology. Much of this speculation can be traced to selective misinterpretations of scientific discussion and, in some cases, to commentary by individuals highlighting perceived anomalies without acknowledging the broader data context. One frequently cited figure in these narratives is Harvard astrophysicist Avi Loeb, who has previously argued that Oumuamua may have been artificial in origin. In interviews and podcast appearances discussing 3I/Atlas, Loeb raised questions about observational gaps and suggested that certain spacecraft images, particularly from Mars-orbiting instruments, such as HiRISE, had not been publicly released. While such claims have fueled online suspicion, NASA and affiliated institutions have stated that data release schedules, instrument pointing constraints, and prioritization protocols routinely limit what imagery is captured and shared, especially for fast-moving objects that do not pose a planetary threat. Within the scientific community, the response to these claims has been measured but firm. No peer-reviewed evidence supports the idea that 3I/Atlas is artificial, hostile, or under intelligent control. On the contrary, the object fits comfortably within existing models of interstellar comet populations, which astronomers expect to encounter more frequently as detection capabilities improve. Indeed, the discovery of 3I/Atlas may be less remarkable for what it is and more significant for what it represents. A glimpse into a population of objects that has likely been passing through the solar system unnoticed for billions of years. With the advent of next-generation survey systems, such as the Vera-C-Rubin Observatory, scientists anticipate detecting many more interstellar visitors in the coming decades. Each will add to a growing dataset that helps refine our understanding of planetary formation, chemical diversity, and the dynamic processes shaping star systems across the galaxy. In this context, the true scientific value of 3I/Atlas lies not in speculative fear or extraordinary claims, but in its contribution to comparative planetology. By studying its composition, structure, and behavior, astronomers can test theories about how material is exchanged between star systems and how common certain chemical building blocks may be throughout the Milky Way. as 3I/Atlas continues its outward journey. Gradually dimming beyond the reach of even the most powerful telescopes, it leaves behind a clear conclusion supported by overwhelming evidence. It is a natural interstellar comet, following a one-time, non-threatening path through the solar system, governed entirely by known physical laws.